Children, welcome to Deeksha Online. In this crash course program lecture, we will discuss mechanical properties of solids and fluids. This important chapter has three parts: mechanical properties of solids, mechanical properties of liquids, and the third part is hydrostatics and hydrodynamics. First, we will take up the mechanical properties of solids. This is also known as chapter elasticity. So we call it as elasticity because this is all about elastic properties of matter. What are all the important features of this chapter? Let us go through this one. First of all, stress. Whenever an object is subjected to an external force, there may be change in dimensions of the force, the change in dimensions of the object. And due to this tendency of change in dimensions, the object tends to restore. This internal restoring force is interpreted in terms of stress. This stress is the ratio of internal restoring force, which is developed inside the object or material, divided by area of cross section. This is the ratio of internal restoring force to area of cross section, or we write it as F divided by A. Remember, this is restoring force, the internal restoring force. So stress is equal to force divided by area. There are three types here. One is what is called as tensile stress. Tensile stress is seen whenever an object is under the influence of a force which tends to elongate an object. This is generally what is known as, first is it's actually longitudinal. In longitudinal we have tensile and we also have something known as compressive. What is tensile? For example, let us take a simple object of a rod which is fixed at one end, and let us put a load on that. For example, I am attaching a load. Then this force, external force, tries to pull it along this direction, while the tensile stress, that is restoring force, tries to pull it along this direction. That's right. Thus, there is a stress. Likewise, if I consider a rod which is fixed here to the wall, and I apply a force along this direction, and the restoring force tries to pull it back. In the case of compressive stress, suppose there is a rod and I try to push it, or let us take a cylinder which is kept on a surface and I am trying to apply an external force. So in both the cases, there is a force which is tending to, you can notice there is a force which is tending to elongate, which is in the opposite direction. This is what is called as compressive stress. This is compressive stress. And the second is what is called as, this is longitudinal, and the second is what is called as volume stress or bulk stress. Here an object is under the influence of a force which tends to compress a given object or say expand a given object. For example, let us take say a cube. Here is a cube on which I apply an external force. For example, you can take this cube inside say a liquid. then the object gets compressed. These are the new dimensions of the object. You can assume that the object has compressed, and thus there is a change in the volume, right? And we can consider one more example. For example, a sphere is pushed inside liquid, it gets compressed from all the sides. There is a change in its dimensions as well. So volume stress is basically the stress developed when forces are extended or say applied from all the sides. The third is what is called as shear stress. Let's try to understand what that shear stress is. Tangential stress or shear stress. So in the case of shear stress, an object is fixed at its bottom, for example here, and we are applying the force from its sides. It is pushed like this. For example, there is a force which is tending to push it like this. You can think of a stack of books one placed over the other, and a force tries to push it from the top. And finally, the shape of this object will be something like this. You will have the new object, or say the object will get this shape. This is the shape of the object. So under the influence of this, the object changes its shape like this. Or you can think of wringing of clothes. So the three stresses are, first of all, tensile, compressive, tensile and compressive, and the second is volume stress, and the third is tangential stress. Now the idea of strain tells us what is the change in the dimensions of the given object. So according to which strain is equal to change in dimensions of the given object divided by original dimension. Again, we have three types here: longitudinal, tensile or compressive, which is equal to change in the length. It may be elongation or it may be compression, change in the length divided by original length, which is equal to delta L divided by L. Likewise, we have bulk strain, which is equal to change in the volume divided by original volume, which is equal to delta V divided by V. So change in volume divided by original volume. Third is shear strain. So in the case of shear strain, the idea is like this. Suppose we consider the previous example. In the previous example, if I take L as this dimension, and let's assume that finally this takes this shape, this is L, this is theta. Let's assume that this is L and this is theta. Then the shear strain is given by tan phi is equal to L divided by L. Tan phi is equal to L divided by L. So this is basically displacement of the upper wire or upper face of the wire or upper face of the cube divided by distance between the two faces. If theta is small, you know how to write. If theta or say phi is small, I will take it as theta. If theta or phi is small, then we can write for small theta, theta is equal to L divided by L. That is the case of shear strain. So shear strain is given by the ratio of displacement of the upper face divided by distance between the two faces, one fixed face and the top face on which the force is applied. Now, whenever a stress is, or say whenever a stress is generated in an object, there is a strain, or say because of strain there is a stress. We can relate each other, of course. Now, if I consider an object, maybe a wire, on which some force is applied, we can find out the relation between the stress and strain, and we can plot a curve between these two. So, what we will do is, we will take a wire and we start applying the force, and we will find out what is the nature of the curve. At the beginning it is linear, the curve is linear, that means within a certain limit the stress and strain are directly proportional to each other. Afterwards, the stress and the strain are not directly proportional to each other. The limit up to which these two are directly proportional to each other is called as elastic limit. This is known as elastic limit. Now, beyond that, the stress strain graph is somewhat like this. This is the nature of the curve, and this is actually elastic region. The first is your elastic limit, the second is elastic up to certain value. That means up to this you can say that the object can get back to its original region. Now, beyond that, the object becomes permanently deformed, and we call it as plastic region. So, there are two regions, one is elastic region and the second is plastic region. In the elastic region, the object can gain its dimensions back. Plastic region, there is a permanent deformation, and the maximum value beyond which the object snaps is called as breaking strength. This is known as breaking strength. And we observe that within certain limit the stress and strain are directly proportional to each other. So, stress is directly proportional to strain, and this is what is called as Hooke's law. So, according to Hooke's law, within elastic limit, stress is directly proportional to strain, or we can write stress is equal to some constant of proportionality into strain. This constant of proportionality, whatever appears here, is known as modulus of elasticity. It's known as modulus of elasticity. So, what is that modulus of elasticity? It is basically the ratio of stress to strain. And this is constant for a given material. It depends on the nature of the given material. It is the property of a given material. So, it is the property of a given material. There are three types of moduli of elasticity. We have, first of all, Young's modulus of elasticity. Which is tensile stress or longitudinal stress divided by longitudinal strain. We can write it like this: F divided by A divided by delta L divided by L. Second is bulk modulus of elasticity, which is represented by B or K, any symbol is used, and this is volume stress, bulk stress divided by bulk or say volume strain, according to which this is F divided by A divided by volume strain is delta V divided by V. Most of the times this happens to be negative, because the object is under the influence of compressive forces, is negative. So, bulk stress is generally treated as negative, or say bulk modulus of elasticity is treated as negative. third is what is called as rigidity modulus or shear modulus, according to which this is shear stress divided by shear strain, that is F tangential divided by A divided by phi. So, these are the three types of moduli of elasticity. These are the three types of moduli of elasticity. There are a couple of important things to be kept in mind here. Suppose I consider, say, a wire. Let us consider the case of a wire. Let us assume that L is the length of the wire, be suspended like this, and let us assume that a weight mg or say mass m is suspended from this wire. Then we can say for this wire, area of cross section being A, Young's modulus is equal to stress divided by strain. What is that stress? It is F by A. This is delta L divided by L. F is nothing but mg, mg divided by A divided by delta L divided by L. A is nothing but pi r square. So, we can write mg divided by pi r square, where r is the cross sectional radius, divided by delta L divided by L. So, for a rod or for a wire, light wire, the Young's modulus can be understood in terms of this equation. Remember, this is a light wire. Suppose I consider a wire which is thick. Let us assume that here is a thick wire, and this thick wire elongates under its own weight. Let us assume that this wire of length L, whose cross sectional area is A, elongates under its own weight. Let us assume that delta L is the increase in its length due to its own weight. Then the increase in its length under the influence of its own weight is given by mgl divided by 2ay. Remember this one. This is mgl divided by 2ay. Many times this equation is also written like this. Mass can be written as density into volume. So, density into volume, that is AL, and this is L, and G is there of course, divided by 2ay. So, notice that this eventually becomes rho G L square divided by 2y. Thus, the increment in the length of a rod due to its own weight is given by this one. So, under the influence of its own weight. So, under the influence of its own weight, the increment in its length is given by this expression. Let us consider one more example. Suppose I consider a gas, and a gas possesses bulk modulus, because most of the times it is the change in the volume. Let us see how does or what is the bulk modulus for a given gas for different processes. For example, let us assume that it is isothermal process. For isothermal process, PV is constant. That gives us PdV plus VdP is equal to constant or 0, differential of this 0. So, we have P is equal to minus dP divided by dV by V. So, bulk modulus is equal to P, because bulk modulus is equal to F divided by A divided by minus delta V by V or delta V by V. And this itself is B. So, F by A has the dimensions of delta P or dP. So, for an isothermal process, this is the equation. What about adiabatic process? For an adiabatic process, PV to the power of gamma is constant. So if I differentiate it, P V to the power of gamma V to the power of gamma minus 1, correct, into dV plus V to the power of gamma dP is equal to 0. And we can simplify it further. Gamma P dV is equal to minus V dP, or we have dP divided by dV by V with a negative sign is equal to gamma P. But left hand side is nothing but bulk modulus, so bulk modulus during adiabatic process is gamma P. You studied it while doing speed of sound in gaseous medium. You may wish to recall Newton's formula and Laplace's correction, etc. deal with this concept. Suppose I consider isotropic process, or polytropic process. For any polytropic process, PV to the power of x is constant. So similarly, I can write x into P V to the power of x minus 1 into dV plus V to the power of x dP is equal to 0. That gives us minus dP divided by dV by V is equal to xp. But this is bulk modulus, so bulk modulus is equal to xp. So in general, we can write bulk modulus as xp. One another important aspect here is the idea of compressibility. What is compressibility? Remember, it's the ratio of or reciprocal of bulk modulus. So we have 1 divided by K or 1 divided by B as the expression for this one. Couple of important results here. Number 1, Poisson's ratio. Sigma is equal to, it is lateral strain divided by longitudinal strain. Let us consider an object which is fixed, or say fixed at one end, or say let us consider a wire, anything is fine, and the wire is of length L. We want to stretch this wire by delta L by applying a force F. Now the question is, how much work has to be done in order to stretch a wire? Some amount of work is to be done. The work done is given by half stress into strain into volume. This is many a times written like this. This is equal to half F by A, strain is delta L by L, volume is AL. So this AL and this L cancel, leaving half F delta L. So work done is given by half F delta L. This can also be interpreted in a different way. Look at this equation. I am going to write as W divided by volume is equal to half stress into strain. But work done increases its potential energy. So I can say energy stored per unit volume, that is energy density. Volumetric energy density is equal to half stress into strain. Half stress into strain gives us the expression for energy density of a solid. One another important result is about a rod which is fixed between two rigid supports. For example, there is a rod whose length is L, coefficient of linear expansion is alpha, and the cross-sectional area is A. Here, thermal stress, you have done it while doing thermal physics. Thermal stress is given by alpha y into delta theta, where delta theta is the change in temperature. And strain, thermal strain is given by alpha delta theta, and thermal tension, that means the actual force, is given by alpha y A into delta theta. It comes from the definition of y. Y is given by F by A divided by delta L divided by L. So, thermal stress is alpha y delta T, strain is given by this expression, while tension is given by this particular expression. So, these are some basic ideas as far as the ideas of properties of solids is concerned. These equations play an important role in solving numerical problems. Keep these equations in mind. Now, let us take up properties of fluids. There are two important properties. One is the idea of surface tension. Second is the idea of viscosity. We will take up surface tension and viscosity one by one. Surface tension is the property because of which the exposed surface tries to contract and it tries to have a minimum surface area. This is the idea of surface tension. Suppose I consider intermolecular forces. Intermolecular forces are of two types. Between the molecules of a given liquid, it is cohesive force, while molecules of different kind exhibit adhesive force. These properties are basically the properties which decide this surface tension. So, surface tension, these are key important things. It is a scalar quantity, and remember, it is always tangential to the liquid surface. It is always tangential to the liquid surface, and surface tension is always produced due to cohesive force, and if the cohesive force is more, surface tension is also more. Whenever the surface area of a liquid increases, the molecules from the interior of the liquid rise to the surface. So, work has to be done against the downward cohesive force. For example, if I consider, say, this idea, this is a liquid surface. Let us consider this way. So, what we are trying to do is, we are trying to increase, say, the surface area of this part. Increasing the surface area means pushing some molecules from inside to the top. Now, pushing from inside to the top requires work. Work against what? Work against the downward cohesive force. Cohesive forces tend to pull it back, and we have to push the molecules, or molecules from inside to the top, as a consequence of which the work done gets converted into internal energy. That is what is nothing but surface tension. Suppose I consider, say, a liquid surface on which we consider a line. Then the surface tension is nothing but the force which is tangential divided by the length of that imaginary line. So, force acting per unit length of an imaginary line drawn to the free liquid surface at right angles to the line and in the plane of the liquid surface is defined as surface tension. So, it is basically force acting per unit length of an imaginary line drawn on the liquid surface. Suppose I consider a couple of important concepts related to this one. As I was telling, the work done gets converted in the form of energy, and this is what is known as internal energy or the surface energy. Surface energy increases by a value T into delta I, where T is the surface tension and delta is the increase in area. So, in fact, we can write surface tension as increase in its surface area, increase in its internal energy or surface energy divided by increase in its area. So, this is the work done. This is the work done to do so. There are many important applications as far as this simple concept is concerned. Let us see what are all the important concepts, important equations, important applications, etc. Number one, in order to do work, in order to increase the area, or say in order to find out the energy associated with different say shapes. For example, if I consider a liquid drop, for a liquid drop the work done is equal to 4 pi r square T, or we can write corresponding increase in the energy is 4 pi r square T. However, for a soap bubble, this W is 8 pi r square T, or delta U is equal to 8 pi r square into T. Let us consider such a big drop. For example, here is a big drop whose radius is r, and we want this to be split up into n identical drops, each of radius r, say. Then again work has to be done. What is that work done? Work done is equal to change in the surface energy, and this becomes change in the surface energy can be calculated, and to find out it we need to relate the radii, and clearly you all know that r is equal to n to the power of 1 by 3 into r. Thus, change in surface energy becomes delta U is equal to 4 pi r cube into T 1 by r minus 1 by capital R. This can be simplified further, 4 pi r square T into n to the power of 1 by 3 minus 1. So, the work done in such a case is given by this expression. If I consider such a liquid drop, or maybe a bubble, or maybe a cavity inside liquid, etc. There is an excess pressure. Suppose I consider this concave side, the pressure on the concave side is greater than the pressure on the convex side. The pressure on the concave side is greater than pressure on the convex side. Now, you may ask, by what value is this pressure greater? This is something like this. Suppose I consider a liquid drop. In the case of a liquid drop, then the pressure inside is greater than pressure outside by a value 2T by R. That means pressure inside is greater than pressure outside by a value 2T by R. This difference is what is called as excess pressure, and excess pressure for such a case is given by 2T divided by R. Suppose I consider a soap bubble. That means this is a surface, or say soap bubble, I will write as soap bubble, and this soap bubble has two surfaces, inside and outside. It is hollow, remember. This time the pressure inside is greater than the pressure outside by a value 4T divided by R, or the excess pressure is equal to 4T divided by R. So the excess pressure is equal to 4T divided by R. Suppose I consider a cavity. For example, you have a liquid, this is liquid, and an air bubble, or say a cavity is generated here. Cavity is nothing but air bubble. Now if you look at it, here again there is only one surface, and accordingly the excess pressure in this case is 2T divided by R. So excess pressure in this case is nothing but 2T divided by R. Thus, for a liquid drop, it is 2T by R. For a soap bubble, it is 4T by R, and a cavity or air bubble in a liquid, it is 2T by R. What do you observe? You observe that if there is one surface, then the excess pressure is 2T by R. If there are two surfaces, then it becomes 4T divided by R. So remember this important concept, a very useful idea for numerical problems. The relative values of the adhesive force and the cohesive force decide, or say give rise to, probably non-flat meniscus. For example, if I consider say a liquid in contact with a solid. If I consider this particular point, this is under the influence of two forces, cohesive force and adhesive force. Adhesive force is by the solid, cohesive force is by the liquid molecules. If the cohesive force is greater, suppose assume that cohesion is greater than adhesion, then the liquid takes this shape at the meniscus. If the adhesion is greater than cohesion, then the liquid meniscus takes this shape at the point of contact, which means that it is not a perfectly flat surface at the point of contact. Suppose I consider this simple case. Let's assume that at the point of contact, the liquid surface is like this. We can draw a tangent at the point of contact inside the liquid. And this angle is what is known as angle of contact. So I drawn a tangent at the point of contact between, or say with respect to the liquid in contact, and I measure the angle between what? Tangent and the plane surface of the solid. This is what is called as angle of contact. That is nothing but the angle enclosed between the tangent plane at the liquid surface and the tangent plane at the solid surface inside the liquid. This is angle of contact. Suppose I consider a concave shape outside it is concave. For example, this is the shape. Then the liquid rises up. That means this time theta is less than 90 degree. You may notice that this theta is less than 90 degree. So angle of contact theta is less than 90 degree if the concave shape is up and the liquid rises up. Suppose you have this case. Then this is the tangent and this is your angle. So this time it is convex shape up and it falls, the liquid falls down, or say there is a drop, and theta is greater than 90 degree. Third case is the meniscus is flat. For example, here you can consider the meniscus to be flat. So this happens and the liquid neither rises nor drops. There is no rise, there is no drop, and it gives rise to theta is equal to 90 degree. So angle of contact is this particular angle. Now we saw that the liquid may rise here, isn't it? For example, if I consider this, there is a rise in the level. Suppose I consider a very narrow tube. If I consider a narrow tube, then what happens is that because of this angle of contact, the liquid level actually starts rising. Actually, it is to balance the excess pressure. So what happens is that whenever a capillary is immersed, there is a rise in the level of the liquid inside this capillary. This is what is called as capillary rise. And that capillary rise H is given by 2t cos theta divided by rho rg. Capillary rise is given by 2t cos theta divided by rho rg. What is that? Rho is the density of the liquid, r is the radius of this capillary tube, r is the radius of the capillary tube, g is the acceleration due to gravity, t is the surface tension, and theta is the angle of contact. This height is measured from the bottom of the meniscus. However, there exists some liquid above this line also. So if the correction is to be taken into consideration, so what happens is something like this. So if I take this into consideration, this is your H, that is what this expression is. But if I take this actual H into consideration, then if this correction is applied, then this T, surface tension, can be written in the corrected form like this. This is rho rg into H plus r by 3 whole divided by 2 cos theta. So taking the correction into consideration, then the surface tension can be written in the following form. One of the very important ideas here is something like this. Let us consider two soap bubbles. For example, this is a soap bubble of radius r1 and there is one more soap bubble of radius r2. Now, let us assume that say r1 is greater than r2, this is r1 and this r1 is greater than r2. Now, when they are brought in contact with each other, what happens is that they form something known as a double bubble. That means it's something like this. And these are their actual surfaces. Now what happens is that the pressure inside the smaller is greater. Now excess pressure is inversely proportional to radius, So pressure inside this is greater and therefore it exerts a greater pressure. Therefore now this is the common meniscus. So this becomes the common meniscus for both of them. So if I consider this bigger sphere, or say the sphere corresponding to the common meniscus, remember this is R2, this is R1. This common meniscus will have a radius R, which is given by R1 R2 divided by R1 minus R2. So this is the radius of curvature of the common surface. So common surface which is in contact will have a radius as given by R is equal to R1 R2 divided by R1 minus R2. So this is basically a double bubble case. That means if you consider two bubbles joining to form a double bubble, this is the case. However, if the two bubbles, for example, if I consider this is a bubble of radius R2, this is another bubble of radius R1. If they combine to form a bigger one whose radius is R, then their radii are related simply by this equation. R square is equal to R1 square plus R2 square, or R is equal to square root of R1 square plus R2 square. So this is the idea behind the combination of bubbles. Another important property of a liquid is what is known as viscosity. Simple idea. Viscous force is nothing but the force between different layers of a liquid. For example, if I consider different layers of a liquid, let's assume that these two layers have a velocity separation delta V, and correspondingly this height is say delta Y, then viscous force is directly proportional to velocity gradient. And Newton's law of viscosity tells us that this force is given by eta A dV or delta V divided by delta Y. For small values, this can be written as dV by dy. So viscous force is given by eta A dV divided by dy. This is what is known as Newton's law of viscosity. The couple of important equations here. Suppose I consider a pipe or say liquid flowing here. Let's assume that Q is the amount of or say volume of the liquid flowing per unit time through a pipe of radius R, across which a pressure of P is maintained. Pressure difference is maintained. Then the amount of liquid flowing per unit time, many times represented as dV by dt, this is volume of the liquid flown per unit time, is given by something known as Poiseuille's equation. So according to Poiseuille's equation, the volume rate of flow is given by pi r to the power of 4 into P, where P is the pressure difference, divided by 8 eta L. 8 eta L. So the volume of the liquid flowing per unit time is given by pi r to the power of 4 into P divided by 8 eta L. You may notice that this is nothing but something per unit time, and this can also be written as P divided by 8 eta L divided by pi r to the power of 4. If you look at it carefully, something which is flowing per unit time is equal to some difference divided by some other term. This resembles the equation electric current is equal to potential difference divided by resistance, or heat current is equal to temperature difference divided by thermal resistance. Just like these two equations, this is pressure difference and this is some flowing quantity, and therefore the denominator must represent opposition offered, which is known as fluid resistance. So, fluid resistance is nothing but 8 eta L divided by pi r to the power of 4. 8 eta L divided by pi r to the power of 4. So, resistance of a fluid, or say fluid resistance, is given by 8 eta L divided by pi r to the power of 4. So, Poiseuille's formula gives us the volume of the liquid flowing per unit time. Stokes' law is another important law which tells us the viscous force whenever an object is in, or say moving with terminal velocity in a fluid. For example, we can consider, say, a liquid. There is a long column, let's assume, and a steel sphere, or say steel ball, is falling down. Let's assume that the steel sphere is of radius r and it is falling at a terminal velocity vt. Terminal velocity means constant velocity. Then Stokes' law tells us that the viscous force is equal to 6 pi eta rv, where v or vt is the terminal velocity. And we can also find out what the terminal velocity is. The terminal velocity is given by 2 by 9 r square into rho minus sigma divided by eta into g, where r is the radius of the steel sphere, eta is the coefficient of viscosity of the liquid, rho is the density of solid, and sigma is the density of liquid. Sigma is the density of the liquid. Thus, we have terminal velocity as given by Vt is equal to 2 by 9 r square into rho minus sigma g divided by eta. Another quantity which is quite important in the present context is what is called as Reynolds number. What is that Reynolds number? It's the number which decides the nature of flow of a liquid. If this Reynolds number is less than 1000, it is treated as laminar flow. And if this is greater than 2000, it is treated as turbulent flow. It is treated as turbulent flow. So, between 1000 to 2000, the liquid may undergo turbulent flow or say laminar flow, all depending on the subsequent conditions. This Reynolds number is given by rho v into d divided by eta. So, Reynolds number is given by rho into v into d divided by eta. So, remember this equation, Reynolds number is generally asked in the conceptual form. So, remember the range of values as far as Reynolds number is concerned. Okay, as far as this part is concerned, this is the synopsis part 1, where we have discussed the properties of solid and properties of fluids. Which two properties? Surface tension and viscosity. In the part 2, we will take up the hydrodynamics ideas, where we have hydrostatics, that is fluid statics, and fluid dynamics for our discussion. Thank you.